Okay, if you could take your seats, please, we'll get the afternoon session underway. Wow, I should have been an elementary school teacher.
You still have time.
Okay, elementary school teachers don't crack jokes. So we're going to have, welcome to the afternoon session. Tuesday we're going to have 3 talks on the SOCCOM program, beginning with Lynne Talley, and then a final talk on global biogeochemical Argo, the prospects for a global program. So I will begin by introducing Lynne Talley, who is one of the PIs of the SOCCOM program and leads the observational component of the program.
Yay. Okay. Thanks, Ken. I'm a spy. I'm a physical oceanographer. So I haven't memorized my chemistry yet. Okay, okay, there's a test at the end of this of me. I have 2 tasks. One is to introduce to you what SOCCOM is, and that'll probably take most of this time, which is pretty short. And then I want to tell you something about what the physical oceanographers and sort of climate side is doing in SOCCOM and some nifty, neat new results. There's our website. You'll see it in a couple other places. What is it all about? It's all about global warming, basically. And these are 2 maps from the IPCC. The upper ocean, it's all heading to heck. It's getting warm. Upper ocean is warming everywhere with some intensification in the northern hemisphere. Why are we interested in the southern ocean? This is the deep ocean warming from Perky and Johnson. I think you're probably all familiar with this map. Showing that it is strongly intensified in the south. So that's a first clue that the Southern Ocean is going to be someplace important to look to understand how the planet is changing. My second sort of motivational slide is the carbon one. This is a slide that many of you contributed to the data sets, as Takahashi annual mean. If you contributed, you know how little data is in there, but we can use the map anyway. Basically, there we are. Outgassing and uptaking CO2, and then one of the maps of anthropogenic CO2 showing us that the Southern Ocean actually has a fair amount of anthropogenic CO2, which you all know extremely well here. These are just motivational. Part of the motivation, though, is to say how do we make these maps with observations and with observations and models. So for motivation, we find sort of 3 big climate facts. One is that the Southern Ocean is taking up a lot of heat. You see a huge range in the percentages, but none of those are under 50% of the excess heat that's coming in from the atmosphere. The second thing is that it's taking up a lot of the anthropogenic CO2. When you integrate over those regions, you'll get about up to half is going into the Southern Ocean. And a third paper I didn't show, a third result I didn't show a slide motivating, but this is Sarmiento et al., that the biological production north of 30 south largely comes from the Southern Ocean, with the exception of the North Pacific. So this is going to be upwelling, old, cold, rotted water with its nutrients. Just very briefly on physical controls on this, why is the Southern Ocean important? This is sort of a 3D overturning circulation from Marshall and Spear, showing our usual North Atlantic overturn up here, flow in at the surface, going down deep, out it comes. And this is NADW being formed from warm surface water. So that's going to have one control on what it can take in. And in the Southern Ocean, because of the Drake Passage effect, instead we have the inverse. We have upwelling of deep water to the surface, and then splitting into the bottom water formation and then into the thermocline up here. So here we're upwelling deep water that's old. Here we're using warm surface water that's obviously very ventilated. So those have very different responses. And that's all physics, Drake Passage effect. The other control on the ventilation is stuff, you all know all this. This is the teaching you do yourselves. There's the map. This is the effect of the NADW production. There's all that uptake up there. Down here, the only way we get uptake is in the subtropical gyres with subduction. And farther south, there's some outgassing going on here where there's upwelling. And you'll be hearing a lot about that in the talks coming up. And then this is the upper ocean. Wind stress curl driving upwelling or downwelling. So we have subduction and we have upwelling. And it's mitigated by topography, where we can get more upwelling. We'll see that if we get to the end of the talk. And enhancement of the stratification of extremely high carbon gradient near the surface where the diffusivity is large. So for SOCCOM, the motivation is that we want to get climate models right, and they're kind of imperfect. We've already heard that. And they're especially imperfect in the Southern Ocean, where it's wrapped around. That's imperfect, too. And what happened? It this out. They're especially poor. Why? We don't know much about what's going on down there. We make measurements in the summertime. So how do you improve? We go and observe. We compare the observations with the models, and we fix the models. And that's what we're doing. So here's the grand challenge we set for this project. The remote and hostile, this person is deploying something over the side of that ship, and this happens often when we're out there, is the least understood and least observed region of the world ocean. So how are we going to go about it? Argo has completely transformed the way physical oceanographers look at the ocean. Our graduate students don't know that data existed before Argo started. Everybody's sort of refining and reinventing a lot of oceanography based on it. So this is a phenomenal system. And it has core principles of measuring, the way it measures and the way data are made available. And so with SOCCOM, we're extending that as basically a big experiment to a very large region for biogeochemistry as well. And here, the things that are new that allow us to do this are the development of biogeochemical sensors by those of you in this room, and especially right there. You're going to hear from Ken. And what we've added to the floats are pH, nitrate, oxygen, and fluorescence and backscatter, courtesy of, I should say, NSF funding for the basic project, NOAA for a large half of the actual floats, and NASA for the optical sensors. Those are our sponsors. And we can also extend measurements under sea ice, seasonal sea ice. And the second thing that's really motivating this is big improvements in models and the ability to do basically data assimilation. It's called state estimation in the form that we're doing it. So we have models, and we have state estimation, we have a way to observe. So here's what we're doing. We're doing observations, state estimation, and high-resolution models. I'm in charge of the observation component, although it would not possibly exist without Steve and Ken building everything to make it work. And our protocol is that these are biogeochemical Argo floats. We have the funding to deploy about 180 to 200, probably going to be closer to 180 over 6 years. They follow Argo sampling, 2,000 meter, 10 days, and we can get under the ice. Ask later how. And we're partnered with Argo. We are very much integrated with Ghost Ship because of calibration requirements for these sensors. And with all of our friends who have research programs out there, and we're looking for you if you have cruises with validation data. State estimation, very important, high resolution, incorporating the observations into this biogeochemical ocean model, the Southern Ocean State Estimate. This is Matt Masloff at Scripps who runs this. And high resolution Earth system models, CM 2.6 is the one that is being busily analyzed, CMIP comparisons. We have a lot of people, numbers. I took a lot of these slides from a presentation, and we all merge we work together. We have a repository of slides. Here are our numbers right now. We also have a lot of undergraduates in the summertime, a lot of us, a lot of institutions. We have a structure at the top. We have 3 areas. We have observations, models, and impacts. And Jorge is the head of the whole thing. There he is. This would not exist without his persistence and leadership. So here we are. And I should mention the 3 themes. He's heading the whole thing. Steve and I are doing that. Ken's the associate. We run the observations. Joellen is in charge of the modeling group, Heidi Cullen from Climate Central for the outreach, and Roberta Hotinsky holds it together. The floats that we put out, I mentioned already what we do. Here's a picture of the sensors. This is a picture of a deployment. There it goes over the side. Put together a slide for ships that are deploying. It's an Argo mission, Argo data management and principles. The data is fully public from the beginning and posted online. Mostly we have UW Apex floats, and we're in experimental phase on Navis floats. It's basically a tech transfer. They are ICE enabled and they have those sensors. There's a first profile from a float. I don't want to leave out the calibration slide because you can't go out there and do this without calibration, at least for a while. And the goal is to get away from it, but here we are. So there's the investigator sailing for, hopefully it's not his last cruise, according to Susan Waples, for a ghost ship line in the South Pacific. She said, bristling with 50 floats from 8 different programs, including ours. Ghost Ship is very much partnered with all of these new float projects. Here's our Pacific array right now. Red is where there are floats already out there. Orange is where we're going in next year. Here's what we have to measure, at sea for calibration, quite a long list. And a lot of this on a non-ghost ship cruise will come back to a lab and be run samples in the lab. So our status of the observing system now is we have 50 operational floats, and we put in about 58 total, so we have pretty good survivability. Ken will talk about that. Putting in 44 this next year, so we're really growing, and here's our map. Data on the website, and there's now a way to get the data over by hand, SneakerNet, basically almost, to the Argo system, and by the fall it will be fully streamed. Here's the modeling plan. We have data, and the data is connected to the carbon system through algorithms that you'll be hearing about from Nancy Williams. And these go into assessing models. And the data also go through the state estimate, which goes into assessing models. And the state estimate and the models feed back into OSSI's, observing system simulation experiments, that help us inform where to put the floats. It sounds kind of circular, but it's working. This is a little bit about SOCCI, the Southern Ocean State Estimate. These are slides from Matt Masloff. Oh, you guys are so happy with these wiring diagrams. I find it very bewildering, all these things that are connected. So Ariane Verity and Matt have implemented Bling 2 in the state estimate, and they've done the adjoint, and it's going. So this is available to people, and there are various flavors of forward models. Highest resolution right now is 1/12. The 1/3 degree is what's shown here, and the 1/6 is what's the workhorse. Here's a laundry list of stuff that's available, which I will skip, but if you're interested, definitely let me know or write to Matt. On to the regular model, the CESM type modeling. This is Joellen's organization of a Southern Ocean Model Atlas to set up metrics for comparing with all of the different models. And there is in development a SOMIP, a Southern Ocean Model Intercomparison Project with protocols that are now being developed and should be finalized, I think, at the September CLIVAR meeting. That's modeling, and then we have a lot of outreach. There's all your favorite ways of looking at the world. This one's mine. This is the actual website, which connects to all of our data. And there's our website address. There's a lot of classroom interaction with this program because it had its origins as a science and technology center. There's a big outreach component built in. On every ship where we've had a grad student or a postdoc, they have been working with a middle school science teacher doing blogging and answering questions with students in the classroom. Been very fun for the people at sea. How much time do I have? Wow, make it. Okay. So that's the program. You'll be hearing more about parts of it in the next couple talks. And then this part, the last few minutes, I just want to share with you some of the things we're excited about in the physical side. What are we up to? There is a publication list on the SOCCOM website that's growing by leaps and bounds. We're kind of open-minded, and it includes friends of SOCCOM. We have a lot of associate investigators, and so we are a very collaborative community, and the results are SOCCOM and other grants. It's a mixture. Okay, what we're looking at as physical oceanographers would be the air-sea fluxes of heat and fresh water. Water mass formation, that means we need to know the buoyancy fluxes, how much is going in and out of the ocean, and what are the rates of formation. We're interested in dynamical balances that we can diagnose out of mostly from the models, but also a bit from the observations, looking at how the effects of eddies, of high resolution, topography, steering, form stress, etc. We have a beginning component looking at floats and how to track floats under ice and what's the circulation under the ice. And I'd say that theme, at least for me personally, is to focus on the asymmetric nature of the Southern Ocean, not its annular sort of ring around Antarctica part, but the regionality is very important. We are deploying floats and modeling in a completely circumpolar sense. That's so that we have a structure to then look at the regions. And we're very carefully trying to understand how the pieces all fit together because we really want to understand how the carbon goes in and out. It's not going to be the same everywhere, for instance, and the heat and the fresh water. Here's the forcing fields that we're all familiar with. This is the wind stress. Color is amount. These are the westerly winds down here, and then there's easterlies. Katabatics come off of Antarctica. It's very important. So there are winds and reversing up to trades. This is a map that you'll see again in Jorge's talk showing the Ekman upwelling in red and downwelling in blue. So we have a wind stress curl effect. So we have a region around Antarctica in the ACC that is upwelling. The bottom two are to represent the buoyancy forcing. This is a sum of the heat and fresh water fluxes, but not including ice, for the globe. And drawing your eye back to the difference between the North Atlantic and the Southern Ocean. Where it's blue, it's losing heat, it's losing buoyancy, it's getting denser. There's the North Atlantic, all getting denser. Southern Ocean, really big contrast, all yellow, almost. We're not seeing the polynya activity along the coast here, but out in the open ocean, we're gaining buoyancy, bringing up deep water and letting it join the circulation. So it's sort of the inverse. How can a high latitude region like this be gaining buoyancy, gaining heat? It gains heat because the cold water comes up, hits the air, and says, oh, I'm colder, I'm going to warm up, and move into the thermocline. And then we'll also see a lot of the buoyancy gain down here is fresh water. Sea ice is very, very important. In the next slide, I'll show you a very recent result. This is the winter sea ice edge. Seasonal sea ice is almost all of that. This melts way back, except in some special areas like the Weddell Sea. So we have a big seasonal area that's perfect for our floats. The Arctic is harder. Southern Ocean, ice melts away, and the floats are going, yeah, okay, I can reach the surface, and I can talk to a satellite now. That's important for the observations. The winds and the curl create a circulation. I don't think I had this animated. This is from Adele Morrison. Who's been a postdoc at Princeton. And it shows you how complicated this can be in a mesoscale model. It also shows you that it's not a ring around Antarctica. It's got continents in it and the deflections in the whole system. So this is important. That's the zonal asymmetry. The overturning circulation, this is a cartoon made following Lumpkin and Spear and Schmitz and Gordon that begins to show us sort of the three-dimensionality of the overturn, that it's not just water in, upwelling and splitting and going down and so forth. It's got three oceans that connect in different ways to the Southern Ocean. The North Atlantic connects by making deep water that rises up. The Indian and Pacific connect by upwelling the bottom waters diffusively and sending them back with their very old water back to the Southern Ocean. That's fertilizing that nutrient, that biological production. And I'm running out of minutes. One? Okay, so wait a minute. I'm not quite done yet. Here we go. 3 new results. I'm going to show you basically the first 2. Number 1 is a paper that Ryan Abernathy did using the SOCCOM analysis with quite a cast of co-authors, just published in Nature Geosciences on the role of sea ice in that buoyancy flux. The second one is one that we're nearly ready to submit. This is a joint between observations SOCCOM and CM 2.6 and CESM, looking at the upward spiral of the deep waters into Antarctica. And the last one is just an illustration of the importance of topography. This is Ryan's paper. Here's the upwelling deep water coming towards Antarctica, splitting into thermocline and bottom water. And from this, he diagnosed that the sea ice has two roles. The same ice has two roles. Here's the fluxes. Where it's purple, the brine rejection is making bottom water. Then the wind blows it out. And by the time it melts, it's melting way out here. So we're actually exporting fresh water from the Antarctic bottom water formation region into the thermocline water formation region. So the transformation is for both of them. And that's really significant and new, that it's the sea ice that does that, not snow, not rain, but ice. It's a fractionation. This is the upward spiral. Here's motivated by the melting of Antarctic ice shelves, which is accelerated over here. Why? Oh, well, we go back to the WOS data, the Orsi-Whitworth Atlas, and we see that warm water spirals into Antarctica. Where does it hit? Oh, where it's melting. So it's not hitting over here, and it's not hitting in here. It's hitting there. And this is pretty darn close in this region, too. And there's a little bit of melting going on there. So using my PowerPoint sketcheroo, you say, oh, it's spiraling. There it goes in. You can look at the depth. Using the actual gridded data from that Alex Orsi provided a few weeks ago, we plotted it. This is the warm water spiraling in from the Atlantic and coming up towards Antarctica. This is a particle release in SOCCOM or CM2. This is a CM 2.6 showing particles coming in and rising to the surface. So this is, I'll skip that one. Sort of important physics being revealed here is that how that water in the models rises to the surface across 1,000 meters is at topographic hotspots. It's not uniform across there. It's in the big eddy areas. That's where it's getting itself up. It's like jiggling it. You know, it just sort of shakes and comes up. That's the way I picture it. Once it gets to 200 meters, it's coming up where we have a lot of variation in the models here. All the models show that. Not all the models show this. This is SOCCOM showing vigorous upwelling over the Pacific Antarctic Ridge. And hydrography shows that upwelling as well. So basically, I'm going to go all the way to the end since we're there. I'd like to just say something really important, I think, about having this teamwork. We have these three really disparate groups. Everybody firmly believes that their approach is the best, which is great, because then we're willing to work together. So then we and listen and talk. So we come in advocating from our side and listen to the other sides and come up with a much better picture. And that is what we're supposed to do, to be able to improve the models. So we're challenging the models by looking at these mechanisms. Where do the models look the same? Where do they differ from observations? I would just say that it's super important that we're collaborating and working together. And we want to say big thanks to NSF and NOAA and NASA. So thank you.
We have time for one question for Lynn. There's also a 20-minute question period at the end. But if there's one quick question while we change over to Nancy.
Can you picture the spiral that you had?
Yes.
Mostly adiabatic, or is that guy pick the process?
Who's
Yeah.
you next?
Nancy's next.
So
Nancy's
I'll hand this
next.
over to her. Yes, right. Veronica is analyzing that in SOCCOM now. It's mostly adiabatic, and we're working out where it's not adiabatic. So this first cut, it's mostly adiabatic. Up at the surface is where it moves away. I think in those hot spots, it's likely to be pretty diabatic. The particles are released over 1,000 to 3,500 meters, big density range. And then we can follow them. We tag them with their density, temperature, salinity, so we can follow that.